Determine the minimum coefficient of static friction needed for the ladder not to slip as a function of the ladder's mass and length, the man's mass and position along the ladder, and the angle the ladder makes with the floor. Assume the friction between the ladder and the wall is negligible. So the man has a mass capital M and he is a distance little d from the bottom of the ladder. And we want to find the minimum coefficient of static friction. In this problem, nothing is moving, so the acceleration is 0 and the angular acceleration is 0, which means the sum of the forces in the x direction is equal to 0, the sum of the forces in the y direction is 0, and the sum of the torques is 0. So we're going to start off by doing a free body diagram for the ladder. Remember that the location of your force vectors is very important for Model 4. So the ladder has a force of gravity which acts at the center of the ladder, and the ladder has a length capital L, and so this distance is capital L over 2. The mass of the ladder is little m, so this force is little m times g. The other forces come from things that are touching the ladder. The man is touching the ladder, and the man is a distance little d along the ladder. So this force, I should make that a little longer. This force is acting straight down. This is capital M times G. And the floor is touching the ladder. The floor exerts a normal force and a frictional force. Nothing is moving in this problem, so this is the coefficient of, or this is the force of static friction, which means this coefficient is the coefficient of static friction, like they told us. So that's the force of static friction, and that's coming from the floor. The wall is also touching the ladder. The wall exerts a force which is perpendicular to the surface of contact, so this is also a normal force. This is the normal force from the wall. The friction between the ladder and the wall is negligible, so there's no friction to put on our free body diagram there. Okay, so now I have all of my forces, and I can do the sum of the forces in the y direction is equal to 0, and the sum of the forces in the x direction is equal to 0. So if the sum of the forces in the y direction is equal to 0, that means the upward forces are equal to the downward forces. Conveniently for us, all of the forces that we have here are either only in the horizontal direction or only in the vertical direction, so we do not have to break any forces down into components. I have one force which is acting in the upward direction, so the normal force of the floor must be equal to the force of gravity that the man exerts on the ladder and the force of gravity from the ladder. Now I can look at the sum of the forces in the x direction, which is equal to 0, which means the leftward forces are equal to the rightward forces. I only have one force acting to the right and one force acting to the left, so the normal force from the wall must be equal to the force of static friction. Because I am looking for the minimum value for the coefficient of static friction, I can use the maximum value for the force of static friction is equal to the minimum value for the coefficient of static friction times the normal force. So we're looking for the coefficient of friction between the floor and the ladder, so this normal force is the normal force that we found here. So for this problem, the normal force is determined by the mass of the man and the mass of the ladder. But if we want the coefficient to be as small as it can possibly be without the ladder slipping, that means we're at a maximum value for the force of static friction. So I can say the force of static friction here is equal to the minimum value for the coefficient of static friction times the normal force, and the normal force, let's write that as capital M plus little m times g. So that's putting that in here and putting this in there. Okay, so I did the sum of the forces in the x direction and the sum of the forces in the y direction, and I still have this unknown value for the normal force of the wall. So now I have to look at the sum of the torques. And I have to choose a pivot point here because I have two forces acting where the ladder is touching the floor. I'm going to choose that for my pivot point, so that will get rid of those two forces from my equation. And the force of gravity for the ladder and for the man, both of those are going to cause rotation in the counterclockwise direction, and the force of the wall is going to cause rotation in the clockwise direction. So I can say the force of gravity for the ladder is acting at a distance of capital L over 2 from my pivot point. And then if this angle here is theta, that means this angle here is 90 degrees minus theta. So this is supposed to be times sine of 90 degrees minus theta. But sine of 90 degrees minus theta is equal to cosine theta. So I'm going to use that to say this is capital L over 2 times m times g times cosine theta for the torque. Then for the force of gravity from the man, the angle is the same. The distance is capital D, the force is capital M times G, so again I can call that cosine theta, since cosine theta is equal to sine of 90 minus theta. And then I look at the clockwise torque, which is coming from the wall, and if this angle is equal to theta, then this angle here is equal to theta, and I have the distance from here to here is the length of the ladder, so this is N, L times N wall times sine theta. Okay, and then I'm looking for the coefficient of friction. I have an equation here with one unknown. I can take this and put it in for N wall and then solve for my coefficient. So I have, let's pull out the cosine theta, so this is capital L over 2 times m times g plus little d times m times g times cosine theta is equal to L times the coefficient of friction times capital M plus little m times g times sine of the angle. Then I can divide by everything that's on this side except for the coefficient of friction to figure out what that coefficient is. So I have L over 2. I have a little g in each term, so that cancels out. So this is plus d times m, all times cosine theta, which I'll take care of in a minute, divided by L times capital M plus little m, and then I'm dividing by sine theta, but I had a cosine theta in the numerator, so sine theta divided by cosine theta is tangent theta, and that is in the denominator. So that is my expression for the coefficient of static friction. That's the smallest value the coefficient can have without the ladder slipping. Then for our question, to see if this makes sense, if theta is equal to 90 degrees, what should the coefficient be equal to? Does your function agree with this observation? Well, if the angle is equal to 90 degrees, that means your ladder is standing straight up like this. I don't know where the man would be in that case. I guess he's standing like that on the ladder. So what does the coefficient need to be equal to? If the ladder is standing straight up, you don't need any friction to keep it standing straight up, but the man would have to be very careful how he balances on the ladder. So the minimum coefficient of friction would be 0. Does your function agree? Well, you have 1 over tangent theta, 1 over tangent of 90 degrees. Tangent of 90 degrees is infinity, so this goes to 0. So yes, it agrees.